Welcome back to the 88 Fall 21 final exam walkthrough. Okay, so in this question, we'll be doing remove multiple. And what it says is, given a list of numbers, you want to remove nodes using that list as a reference. So if you get a list 2, 7, you keep the first node, but then remove next to the node after that, and then remove the next 7 nodes. Okay, so let's look at the doc test. Specifically, it says that this is a generator. And so therefore, we're going to have to yield values instead of just returning them. Okay, so let's look at the doc test with a link, which is A, B, C, D, E, and F. When we call remove multiple, it keeps the first link, but then it removes the next one because the first element is 1, which means we remove 1 here, and then we keep the next one, but then we remove 2 because that's the next one in our list. So we remove D and E, and finally we're left with this F. And as you can see, now link is A, C, then F. Let's look at the second doc test. It says if the sum of the numbers in number to remove is more than number of nodes in link, remove as many nodes as you can. Okay, so proceeding similarly, we keep the first one, but then our first element is 1. So we remove B, we keep C, but then we remove 2. And then we keep F, and we can't actually remove 3 or 4, so we just end there. And we can see we still have the same result, A, C, and F. Okay, so the first question that I'm going to have to ask myself is, what is my condition to stop trying to remove from the list? And the first thing I can think of is if link is link.empty. And if that's the case, then I'm at the end of the list, so there's nothing left for me to do. And in the same regard, what if link is link.rest rather is link.empty? Well, it's probably the same case here because now there's nothing left to remove in the sense that there's no next node. The node I'm currently on would be the one with some value. So in this case, let's say it's the link F. And then the rest is link.empty. So there's nothing left to remove after that. I can just kind of stop. And then the other thing I can potentially think of is, what if I run out of things to, or rather a number to remove from the list that gets passed in as a second argument? So what if I only, for example, had a list with 1 in it? Then I wouldn't want to continue removing 1 from this rest of the list. And so if, or in this if statement, or not number to remove, which allows me to check that if there's no more amount of numbers to, if there is no longer a number of nodes to remove from the list, then my job is done and I no longer have to mutate the list. Okay, cool. So now we can maybe think about the else statement and specifically what the for loop might do. So I want to think about what this for loop can potentially do. So for loops will repeat something multiple times, and something that I might need to repeat multiple times is skipping a link. In this case, maybe 1 times or 2 times, or for the other case, 1, 2, or 3, or 4 times. So very likely, I'm going to be having to use iteration and this for loop in order to actually skip my links. So how do I know the amount of times I want to skip a link? Well, that's based on the number to remove list. So I'll just, first of all, start with the first actual element in it. So for I in range, number to remove of 0. So what this allows me to do is repeat an action, say 1 time or 2 times, or 3 or 4 in the case of the second doc test. And now I want to think, how can I actually skip links and what the necessary precondition is for me to actually be able to skip a link? Well, in order to skip a link, I have to make sure that there is a link to skip, right? So I need to make sure that link.rest is not link.empty. Okay, And if link.rest is not link.empty, then I can go and skip that link, which I can do by saying link.rest is equal to link.rest.rest. And what this would do is, let's say I have a link with A, B, and C. When I do link.rest is equal to link.rest.rest, that means that this pointer no longer points at B, but rather points at C. And so therefore, this middle pointer of this B is kind of erased in some sort of sense. And what we are left with is just A pointing to C. And we've effectively removed the B node. Okay, so why does the else statement make sense? Well, if link.rest is link.empty, then even if we have more things to remove, well, we have to stop because there's nothing left to remove. Okay, so it looks like we're done with almost everything except now just the recursive call. So what do I want to pass in for link? Well, from the doc test, I noticed that I wanted to keep A, but then remove 1, and then keep C, and then remove 2. So I have this alternating fashion of keeping and then removing based upon number to remove. So therefore, if one running of this for loop represents actually removing 1 node or 2 nodes or 3 nodes, or how many are in number to remove, then the next thing I actually need to do is skip a node so that I don't end up accidentally just removing like, let's say 3 nodes all at once, and instead leave these gaps where I actually leave one. So what I would want to do is link.rest. Okay, and then the second argument has to be number to remove in some capacity. And because I'm done with the zeroth one, so in the first doc test, because I've already removed 1 node, now I just have to do the same for the rest of the amounts of the number to remove. So what I can do is I can do number to remove, and I can just take everything from 1 onwards. So in the case of the second doc test, that would cause me to get this list of 2, 3, and 4 so that I continue with removing elements. Okay, so that's the end of part A. I didn't write it in the skeleton below, but it's the same idea. And now for part B. So as the length of linked rows, what is the time complexity of the remove multiple function? So as we can see, it looks like that there isn't going to be a lot of extra iteration or anything that happens when we make the link longer, but there might be more link.rest being called and more recursive calls such that we can progress through the list. But if we look at it, there's kind of a one-to-one correspondence in that I might have to make another recursive call, or I might have to do another link.rest equals link.rest.rest. And the reason is just because I'm not doing anything extra except going through that list. So therefore, if I add another node, then I'll just have another node to go through. So one-to-one correspondence, and therefore a linear time complexity, because I just have another node to go through if I increase the length by 1. So if I increase it by n, then I have n more nodes to go through, and therefore a linear runtime. So that's the end of this question. Thank you for stopping by.